Well, welcome back. This is part 2 of our presentation on maximum circuit current. And in this part, we're going to talk about PV circuit maximum current in a little bit more detail. So we'll talk about how to calculate maximum current for PV source and output circuits. So starting with source circuits, we're going to look at calculating our maximum current per the National Electrical Code guidance that we find in 690.8 A1, A1, and 2. Maximum current for source circuits, PV source circuits, is going to be our module short circuit current, the module ISC, times 1.25. And again, that 1.25 is an additional irradiance factor. It's a safety factor to account for anytime the module is seeing a radiance above 1000 watts per meter squared. So keep in mind, for bifacial PV modules, this calculation might not be appropriate. So remember, with bifacial modules, they collect irradiance on both the front and the back sides, and so their output current, their maximum output current, may be considerably more than what their STC short circuit current rating is, and we may need to get a little bit more of an accurate safety factor on the output current for bifacial modules. So definitely consult the manufacturer to make sure you're sizing your wires correctly and your whole system design is sized correctly when you're using bifacial PV modules. And you'll probably need to consider evaluation by an engineer when you're working with these kinds of modules. There isn't really a standard way of doing these calculations, an industry standard way. So you need to have, in most cases, an evaluation by a professional engineer. Which leads nicely into the second option for calculating PV source circuit maximum current. Our second option that we're allowed to do in the National Electrical Code is for systems that are larger than 100 kilowatts of generating capacity, 100 kilowatts or greater, we're allowed to do an alternative calculation for our maximum current. And so there's some requirements to be able to do this in addition to the generating capacity requirement. You have to have a licensed professional engineer perform the calculation, or at least review the calculation and sign off on it and stamp it. It has to be a stamped design, and it has to have thorough documentation about the calculations that were used. And you have to use an industry accepted method for calculating your maximum current if you're going to use this option. So for example, with bifacial modules, this is one case where that might make sense to run an alternative calculation to get a more specific maximum current based on the site conditions, the irradiance that's going to be seen on that particular site, and really dial that in terms of making sure you're able to size your wires correctly and your overcurrent protection devices along with the rest of the system design. So the NEC gives us an example of what an industry accepted calculation method would be, and it's called the photovoltaic array performance model. And so there's a bunch of different approaches, and you can check out what that is if you're interested in exploring that further. That's a bit beyond the scope of this particular course, but just wanted to mention that as the NEC does give us that example of what one type of industry accepted calculation would be for this particular context. So looking at an example for our option number 1 here, we have a module short circuit current of 8.91 amps, and then our maximum current for a single PV source circuit is going to be 8.91 amps times 1.25, which gives us a total maximum current of 11.14 amps. So that 11.14 amps is the number that we're going to use to size our conductors, our fuses, and our circuit breakers. Moving on to PV output circuit maximum current, we will look to NEC 690.8 A1B for guidance on how to calculate maximum current of PV output circuits. And NEC tells us that our maximum current for our PV output circuits is going to be the sum of parallel connected PV source circuit maximum currents. So what does that look like? Well, we see in this picture over here on the right, we have multiple PV source circuits coming into a combiner box and leaving on as a combined amount. And so when we combine in parallel, the current's going to add. So we're going to see we have PV output circuit here is going to be 2 parallel conductors per polarity. So this is going to take all of the PV source circuits and combine them into a PV output circuit, which happens to have 2 parallel conductors per polarity. So one circuit, but 2 parallel sets of conductors that we see here. So our example in this case is going to be our module ISC that we saw on the last slide, 8.91 amps. Maximum current is going to be checked as our single PV source circuit first. That's going to be our starting point. So we're going to take 8.91 amps times 1.25, get that 11.14 amps of maximum current for a single PV source circuit. Calculated that on the last slide. Just going to go through that again here. And then our maximum current for 24 parallel PV source circuits. So that would be, if there were 24 of those PV source circuits coming into that combiner box, we would take 11.14 amps times 24, and that's going to give us 267.36 amps. That's going to be our maximum current for our PV output circuit. So that's the end of part 2. Take a quick break and come back and join us for part 3 when you're ready.